Okay. So, um, then I guess we should start with settle down now. Settle down. Okay. So let's start with the homework this time. And I guess the homework, you started doing renewal theory, which is a generalization of the Poisson process. And I think some problems that are pretty good problems. So we have some stuff to do. Okay. So before we start, I guess we can say that sort of so the process N of t is called a renewal process if it's a counting process. So it's a counting process. I.e., so N of t is equal to the maximum N such that Sn is less than or equal to t. And Sn is equal to the sum of n IID random variables. Now these are IID, but as opposed to the Poisson process, these just follow some kind of distribution f. It doesn't have to be exponential. So that's just the. So we see how it's directly just a generalization of the Poisson process. So that's just a little intro. So now let's start with problem 1. So we want to see which of these three statements is true. So N of t less than n if and only if Sn greater than t. Okay, so we want to see if each of these statements is true or false. Now, it's a pretty easy problem, so I hope I'm not boring you. But so we have this time interval 0 to t, and the one thing we definitely know, and it's in the book, and it's a very useful property, it's a very important property, is the following: that we have at least n events occurring in an interval 0 to t, if and only if the arrival time of the nth event is less than or equal to t. So this is what we know. Now, given this information, we can immediately say that A is true, right? Because A is just the negation of both of these. So the negation of, we know that if A is equivalent to B, then not A is equivalent to not B, right? So this is all that's happening here. Now, B and C, on the other hand, are not true. And we can easily sort of come up with examples where they're not true. Since well, B is obviously not true. I mean, say that you have, so for B, say that i.e. n of t is equal to 0, Oh wait. N of t less than or equal to n. Yeah, no. So say that for part B, say that the nth event happens here. And say that we have exactly n events happening in the interval 0t. So n of t is equal to n. Sn is strictly less than t. So obviously this is not true. And similarly here, well, so if n of t is greater than n, so say that we have something like Sn plus 1 here. No, this is n of t is less than n, is greater than n. So oh yeah. So this is also not necessarily true, because say that Sn again occurs before time t, then again no events can happen here. So you can be stuck with exactly nt is equal to n. So this is not true. So I don't think we need to. Yeah. I don't think we need to spend more time on this. But the point of this exercise is to just remember this property here, because this is a very important property. Okay. Now let's do problem 2. So here we have the interarival distribution is Poisson with mean mu. So we have a renewal process where xi's are Poisson mean mu. So what does that mean? It means that Sn, which is just defined, which is the nth arrival time, which is the sum of the first n inter-arrival times, will be Poisson n mu. Why is that? Well, because the sum of independent Poisson random variables is again Poisson with the mean, the sum of all the means. So what do we want to calculate here? So okay, we found the distribution of Sn, and now we want to calculate. So what is the probability that we have exactly n events in some interval? Well, we can now rewrite this as the difference of the probability of n of t being greater than or equal to n minus the probability of n of t being greater than or equal to n plus 1. Since n of t is Poisson is a discrete random variable, the difference of these two probabilities gives us the probability of n of t being exactly equal to n. And now we use the nice equivalence that we have over there. So because we don't know the distribution of this is what we want to calculate, but we do know the distribution of Sn. So this is the probability of Sn is less than or equal to t, minus the probability that Sn plus 1 is less than or equal to t. So, okay. So now, of course, t doesn't have to be an integer, right? So we'll have to account for that in the calculation of this probability, because this is just equal to the probability that Sn is less than or equal to the floor of t. The floor is just the first integer that is less than or equal to this number. And similarly, the same applies here. So now we just sum all the probabilities from k equals 0 until the floor of t. And Sn is Poisson n mu. So this is e to the minus n mu times n mu to the k over k factorial minus sum k equals 0, the floor of t, e to the minus n plus 1 mu times n plus 1 mu raised to the kth power over k factorial. So any questions here? I think this is pretty simple. And the only sort of trick is to realize that, to remember the equivalence between the event that n of t is greater than or equal to n with the event that Sn is less than or equal to t. And then everything's easy. Okay. Okay, so now we'll do problem 3. So we have a renewal process, and its mean value function, so expected value of n of t, is equal to t over 2. And we're asking we basically want to find out what is the distribution of n of t, but so what is this? So first of all, we note that there is a one-to-one correspondence between the mean, when you have a renewal process, there is a one-to-one correspondence between a mean value function and the interarrival distribution. So we have a one-to-one correspondence between m of t and f. And we can prove this in numerous ways, and I guess Professor Witt has already done this using Laplace transforms. So can be proved using Laplace transforms and the fact that m of t is equal to the infinite sum of the convolutions of f. But that's really not that important. I mean, all that we sort of need to remember is that if you know m of t, you know f, and vice versa, because they're uniquely determined. So let's see. So let's guess that n of t, or that, let's actually guess that f of t is exponential with rate 1 over 2, which would make the xi's exponential with rate 1 over 2. Two or 1 over 2? No, 1 over 2. So in other words, n of t would be a Poisson process with lambda equals 1 over 2. This guess, then this would lead to m of t is equal to the expected value of n of t, which is equal to the expected value of a Poisson random variable with mean lambda times t. So this is t over 2. And this gives us the right result. So, and now by the uniqueness of by the one-to-one correspondence between m of t and f, we can say that we verified that the interrival distributions have to be exponential with this rate. But now, I guess if we also, another way to do this would be, so this is sort of extra here. Sort of another verification is that we know that m of t can be given with this nice formula. M of t minus. And this we can easily derive by just conditioning on the time of the first event. I think it's done in your book as well, but you just condition on when the first event occurs, and then you have, and well, probably don't need, well, this just comes out from this. So, right. But anyway, so now given this formula, we want to see, is it true that t over 2 is equal to integral t minus x over 2 times 1/2 to the minus x over 2 plus 1 minus e to the minus t over 2. And now, I won't do this because I don't think it's worth our time, but if you go ahead and calculate this integral, do by parts or something, then you will see that the two sides are equal. So this is true. So that's just another way of doing this. So are there any questions on this? Okay, then we can move on. So now do problem 4. So we have two independent renewal processes. And we take a new process, so which is the sum of the other two. So it's like the superposition of the two renewal processes. And we want to figure out three things. So do we have, does n of t have independent inter-arrival times? Are they identically distributed? So and thirdly, is n of t a renewal process? Okay. So the answer to all of these questions is, of course, no, as you've already seen in the solutions. And the example that Professor Witt gives is very good, actually. So let's write this first. No, no, no. So for part A, if we consider so let's say that n1 of t is Poisson process with lambda equals 1, and n2 of t is just a deterministic renewal process where we just know that every inter-arrival time has length exactly 1. So n2 of t, what we know is that the xi's are just identically equal to 1. So in this case, okay. So let's see. Let's assume that, the first. So now we're taking the superimposed process, and let's say that the first event occurs at time 1/4. So this is x1. Then what does that tell us about the second one? Can the second inter-arrival time be greater than 3/4? There's no way, right? Because of the second process, we know that no matter what, we will have to have an event occur at times 1, 2, 3, 4, and so on and so forth. So in other words, knowledge about where x1 happens, or where s1 happens, gives us information about the distribution of x2. So x1 being equal to 4 implies that x2 has to be less than or equal to 3/4. And that's just one example. I mean, you could come up with thousands. I don't know, a lot of them. So they're definitely not independent. Knowledge of one inter-arrival time tells you something about what the next one's going to be like. So okay. And now this example also works for B. So because, again, the distribution of x1 would be, the minimum of an exponential with mean 1 and the scalar 1. Now, the distribution of x2 would be the minimum of an exponential with rate 1 and of the scalar 1 minus x1. So we can actually write this. So part B. So x1 is distributed as the minimum of an exponential rate 1 and the scalar 1. Now, x2 is distributed as the minimum of, again, an exponential 1, and now 1 minus x1. Or, I mean, actually, no, in this case it is, but yeah. Let's not write this, because what if we don't have an interrival? No, actually, just trying to be precise. So if x1 happens here, then it's the minimum of an exponential in 1 minus x1. But what if, so this is the right way to put it. So this is kind of overkill, but there's definitely, yeah?
I understand why x2 is the minimum of exponential with rate 1, because aren't they all 1?
What's that?
I don't understand why it's not the minimum of 1 and 1 minus.
Why x2?
Right.
Okay, yeah. So the question was, why is x2 distributed the way it is? Well, just look at this picture here. The first interrival time will be the minimum of whatever process 1 gives you and 1. Okay? So we agree on that. Now, the second interrival time, it could either happen here, or if it doesn't happen between 1/4 and 1, it will happen at exactly 1. But now, this interval is not 1 anymore. It depends on what happened in the beginning, what happened with the first interrival time. So if x1 occurred sometime before 1, so if it occurred, say, at time 1/4, then the second interrival time will be the minimum of another exponential or the remaining length of this interval. And the length of this interval is determined by x1. And now, of course, if the first event did not happen because of process 1, and if it happened only because of process 2, then everything sort of starts over, because the exponential is memoryless, and we know that we'll have another event at time 2, so then it is the same. And now, from A and B, it's definitely not a renewal process. So, any other questions? Okay. Oh, and I guess a thing to note is that these three properties do hold, but only in the case when both n1 of t and n2 of t are Poisson processes. And that's, we can prove that, I guess, but we don't have to. Okay. Let's do problem 8. So a machine in use is replaced by a new machine either when it fails or when it reaches the age of t years. So if the lifetimes of successive machines are independent with the common distribution f, show that the long run rate at which machines are replaced equals this, and then part B. So in general, if n of t is a renewal process, then we know that two things. That n of t over t converges to 1 over mu, where mu is the expected value of the inter-arrival times. And we also know that m of t over t will converge to 1 over mu. So in other words, the long run rate, I guess, at which we have events, or is that? Yeah, the long run rate at which, events of this renewal process happen is roughly the reciprocal of the mean inter-arrival time, which makes a lot of sense, right? Because if for example mu is huge, that means that there is a very sort of big gap between events. So we would expect that we get very few events, like in the limiting case. So these are two important theorems. And this is what we'll use in our case, in this problem. So a machine is replaced. So let's view machine replacements as renewals. So then, if we do this, then the inter-arrival time between replacements will be distributed as the minimum of an exponential random variable with no, sorry, the minimum of, it's not exponential necessarily, minimum of whatever this f is, let's say the lifetime. So L is the lifetime of machine, and it's distributed according to some distribution f. We don't know what it is. So we know that we'll replace a machine either when it fails or when it reaches an age of capital T. So this doesn't look very good, but yeah. So this is, and we know that these inter-arrival times are independent and identically distributed. So we know that we have a renewal process on our hands. So now all that remains to do is to figure out what mu is, right? So we need to find mu. So let's see. So expected value of xi is equal to, okay. So now, if the lifetime of the machine is less than t, or equal to t, then that will be the replacement time also. So it's x times fx dx. And now, if the lifetime supersedes t, then we know that we'll have to stop at t. So, and this happens with probability 1 minus big F of t. Actually, this is the right way to say. And another way to sort of write this maybe a little more clearly is that xi is equal to L. I don't know if you've seen this notation with indicator function that L is less than or equal to this big T plus T times the indicator function that L is greater than T, where the indicator of equal to 1. And now given this, we take expectations, we see immediately why the expected value of xi is what it is. So now, hence, so mt over t, which is what we're looking for, will converge to 1 over mu, which is 1 over expected value of xi. And that's what we wanted to prove. So any questions on this? So now for part B, we want to figure out the long-run rate at which a machine fails. So now we're not interested in the rate that a machine is replaced, rather just the rate at which a machine fails. So now we consider the number of failures as a renewal process. And now xi is just the time between successive failures. And again, this will be a renewal process because these interrival times will be IID. So let's see. Let's see. Let's just call this x. So now if our machine, if the machine fails before time t, then we know that, well, you definitely get a failure then, right? So this is L times the indicator that L is less than or equal to t. But now, the more interesting case is what happens if the lifetime of the machine is greater than t. Well, in that case, the machine is replaced by a new one. So the everything sort of starts over again, right? So if the lifetime is greater than t, then, well, we know that this time has elapsed. We replace the machine, and we start over again because we have a fresh machine, and the time until the first failure will be, again, whatever it is here. Is this clear? I mean, another way to say it would be that x is equal to L Actually, this is x given L. Okay? So let's actually move here. So then the expected value of x, we just take expectations in this expression here. So it will be, as before, x times fx dx, the integral from 0 to t, plus the expected value of x plus t times 1 minus f of t. So now we do some rearranging, and we get that the expected value of x is equal to and then we take the reciprocal of that and get the long run rate. So any questions? No questions? Okay. Now let's do problem 21. So problem 21, I think, uses what's called as the renewal reward theorem. So let me just write that the way it's written in the book. So basically, if n of t is a renewal process, and we assume that every time that an event of this renewal occurs, we get some kind of reward. So say Rn is the reward given on nth event. And then we also know that these rewards are IID. And then if we want to count the total reward that we have been given up to time t, then this will just be equal to the sum I equals 1 to till n of t of Rn. And now where the renewal reward theorem comes into play is that we know that the long run rate, or the long run average sort of reward that we get will converge to the expected reward over the length of a cycle and similarly the long run average reward will converge to, again, the same thing. So this is basically like saying that the long run average reward is equal to the ratio of the average reward we get at any given time divided by the length of a renewal cycle, which is sort of makes sense, right? So this is a very useful sort of theorem that we use over and over again in many applications. Because a lot of times, you're interested in a long-run rate of something happening, and the way you easily model that is by imagining that some kind of reward happens whenever you get an event of that type. So, blah, blah. But, so let's go to the problem now. So now we have a single server bank for which customers arrive in accordance with the Poisson process with rate lambda. So here n of t is Poisson process rate lambda. And now there's only room for one person. It's single server, actually. So we have an M general distribution, room for one server, or there's one server and no waiting room. We want to find what proportion of time okay. So the way to do this is that, okay, first of all, consider the renewal cycle to be the time between successive entries. Because we know that people arrive and they will only enter the bank and start to be served if there's no one in the bank. So person arrives, he's served, he leaves, then someone else arrives, blah, blah, blah. And if people arrive in the meantime, they just don't go in. So these are our renewal cycles. And now we use the renewal reward theorem, because now assume that a reward of 1 is earned whenever someone is being served. Okay? So, in other words, what we want to find, the long-run proportion of time that the server is busy would be this, would be the limit of R of t over t. Okay. Well, now we're in luck because, or I guess maybe we want the expected. It doesn't matter. They both converge to the same thing. So then we know that RT over T will converge to the expected reward during a cycle divided by the expected length of the renewal cycle. Right? Now, what is the reward during a cycle? Well, we earn a reward of 1 whenever someone is being served, right? So this means that the expected reward is the expected service time of someone in the bank. And that is just the mean of this distribution G. Now, on the other hand, the expected length of a renewal cycle is not only the person's service time, but it's also the time that it takes someone to arrive. So here we'll have 1 over lambda plus mu G. So this is a good application of the usefulness of the renewal reward theorem. Are there any questions? Yeah.
We just calculate the mean time between entering customers. Isn't that just the mean of the Poisson plus?
No, not really. The question was, is the mean time between entering customers the inter-arrival time of the Poisson process? And it's not really, because we know that the person arrives, he starts being served. Now, then if someone arrives while the person is being served, he doesn't enter, because there's only room for one person.
I mean, if we just plot it up and say that the mean service time is mu G, and then this person has finished service. The time until till the next customer comes is just mean of the Poisson, right? So it's just mu G plus 1 divided by alpha.
Yeah.
So isn't the rate of the entering customers 1 divided by that quantity, or
The rate of an entering customer would be, it would be that, the rate of an entering customer.
no, this problem.
It actually wouldn't, 1 over, it would be that,
So can't you just divide the Poisson rate divided by the rate of the service time?
Divide the Poisson, let me see if I'm, so you're saying the rate at which people arrive is 1 over this.
Yeah.
And then you want to divide this by the rate at which people are served?
I mean, we know the rate that people come. I mean, it's just the arrival rate is just Poisson with alpha divided by alpha, right? But actually, the rate is alpha, right? People just
You want to say that, you want to call this alpha?
No. We know the arrival rate of customers.
Yes, yeah.
So, and the can we just use these two quantities, the arrival rate of customers and the arrival rate of served customers, to calculate this probability?
Well, that's sort of what we're doing here, right? I mean, all that we're saying is, this is really sort of common sense. We're saying that if we take cycles to be the time between a customer enters, we know that the mean time of this cycle is this, because it takes roughly 1 over lambda for someone to arrive, and it takes mu G for that person to be served. Now, during this cycle, the time of which the server is busy is the service time. And the average service time is mu of g. So it makes sense that in the long run, the probability that the server is busy at any time would just be this. So, yeah.
Do you do that as a birth-death process? Just two states?
Yeah, I'm sure you could. Yeah. Yeah, definitely. Yeah. In fact, it might be more straightforward to do it that way. Well, actually, not. I don't think actually you could do it, no, because for continuous time Markov chains, you need to assume that things are exponential. So it wouldn't work here. If the service time were exponential, then still it wouldn't work, because that would make it again. But, yeah.
Service time works exponential?
Oh no, then it would work.
Yeah.
It would work, because the transition rates, yeah. It would work. Any other questions? Okay. Okay, let's do problem 22. Problem 22 is an excellent example of renewal reward. So the lifetime of the car has distribution H. So lifetime distribution H. And Mr. Jones buys a new car as soon as the old car breaks down or reaches an age of T years. The new car costs C $1, an additional cost of C $2 is incurred whenever a car breaks down. Okay. So we want to find the long run average cost. Long run average cost. Now, we can say that this, by using again renewal reward, this is the expected cost per cycle. And I'll be specific about the cycle in just a little bit. Divided by the expected length of cycle. Okay. Now, first of all, what is a cycle? What are we talking about? So let's say the cycle is the time between successive replacements of the car. And then the cost is the cost incurred during that cycle. Okay, and let's actually denote this by x. And these will be the inter-arrival times of our renewal process. Okay. So first of all, let's see what x is. Well, x is will be equal to the lifetime of the car if the lifetime is less than or equal to t, or it will be exactly equal to t if the lifetime is greater than t. Okay? And now, let's see what the cost of a cycle is going to be. Okay. Now, I guess... So a new car costs C$1, and an additional cost of C$2 is incurred whenever a car breaks down. Okay. So here, in the event that the car breaks down before time t, then we incur a cost of C1, but also C2, because of course we have to buy a new car, and we also have to pay for whatever damages the old car sustained. And now, if the car does not break down, and instead it's just replaced at time t, then we know that, okay, we still have to buy a new car, but we know that we can also resell it for a value of R of t. Yes?
You don't sell the car if it breaks down before time t.
Oh no, you don't resell the car then, because it's broken.
Yeah, I think that C2 was the fixing cost.
C2 is just the cost that you have to pay because it's broken. You don't have to pay it if it's not broken. Maybe it's some kind of insurance cost or something, I don't know. And you don't have to pay that if your car just reaches the HT. So then it would make sense that the long-run average cost, again viewed as a renewal reward thing, would just be the expected cost during the cycle divided by the expected length of a cycle. And so this is just C1 plus C2 times f of t minus R of t times 1 minus f. Oh no, this is h, I'm sorry. And the expected cycle time is, as before, x times hx dx from 0 to t plus t times 1 minus h of t. Let me actually make sure that this is right. I think it is, but... Oh, I forgot the C. No. Yeah. Yeah. So this is again another sort of useful application of renewal reward, where it's implicit that you know, the reward here is whatever you need to pay during the cycle. Now it's a cost, of course, but. Any questions? Now, problem 23 is a very easy thing where you assume that H is some uniform distribution, and then you you want to see what value of t will minimize your long-run average cost, and you just do some calculus and figure it out. Okay, so now let's do the last problem I had in mind, which is problem 9. Okay. So worker sequentially works on jobs. Each time a job is completed, a new one is begun. Each job independently takes a random amount of time, having distribution f to complete. However, independently of this, shocks occur according to some process with rate lambda. Whenever a shock does occur, the worker stops working on the present job and starts a new one. And in the long run, at what rate are jobs completed? Okay. So let's define certain things first. So t is the time to complete a job. W is the time to complete the first job that is attempted. Because of course, we could start working on something and then a shock occurs and we have to give up and start working on a different job. And let S be the time of the first shock. Oops. Okay. So we want to find the expected value of t, basically. Okay. Okay. So the first thing to note is that job completions correspond to renewals. Why is that? Well, it's exactly because the shocks occur according to this Poisson process. So let's see. Let's see what this quantity is. So expected time to complete a job, given that the time to complete the first job that is attempted is equal to little w. Well, we don't know. We really sort of don't know what this is. So we condition on what the time of the first shock is. And we know that shocks occur according to a Poisson process, so the interarrival times are exponential with rate lambda. So the density is just lambda times to the minus lambda s ds. Let's actually be consistent. X. Okay. Now, why do we do this? Well, because this quantity is easier to work with. In particular, okay. Now we differentiate between two cases. So if, say that x is greater than w, so if the first shock occurs after the time that the first job has been completed, that was attempted has been completed, well then we know that the time it takes to complete that job is equal to w. Because then like nothing really happens. The shock does not play any role. Now, if the shock occurs before the completion time of the first job, then we will have wasted all that time. So we will have wasted time x, and then we need to start over again. So we need to do the same thing over again. So is this clear to everyone? Okay. So then the expected value of t given w is equal to little, or given w, whatever. Then we can break it up into two parts, right? It's the integral from 0 to w of x plus expected value of t times lambda e to the minus lambda x dx plus the integral from now w to infinity of just w lambda times e to the minus lambda x dx. So now we can do calculations here, and let's actually do some of them. This is plus so is this, I think it's pretty clear, right? And now if we do this integral with by parts integration, it's not too hard to do, then we will get that this is equal to the expected value of t plus 1 over lambda times 1 minus e to the minus lambda w. And then we rearrange stuff, and or actually we take then expectations over w, but t is expected which is then equal to equivalent to expected value of t is equal to the expected value of t plus 1 over lambda times 1 minus the expected value of e to the minus lambda w, which then implies that expected value of t is equal to 1 minus expected value e to the minus lambda w divided by so that's that. Any questions? And of course the rate is 1 over that. Well, if there aren't any questions, I'll see you next week.